The smartphone in your hand, the AI chips reshaping our world, the autonomous vehicles driving into our future. All of these cutting-edge technologies begin with one of the most common substances on Earth, sand. But the journey from ordinary sand to a silicon wafer capable of holding the world's most powerful AI chips requires extraordinary technology and a remarkable process. Today, we'll follow that journey, step by step, from sand to the perfect silicon canvas for the next generation of semiconductors. It all starts with sand, specifically silica, or silicon dioxide. Silica is rich in silicon, but far too impure to use directly. First, oxygen and impurities are removed to produce metallurgical-grade silicon. But even that isn't nearly pure enough for semiconductors. The silicon is then reacted with hydrogen chloride gas, converted into liquid form, and purified through multiple rounds of distillation. The result is ultra-high purity polysilicon. The required purity? 99.9999999999%. 11 nines. That means impurities are controlled to less than 1 part in 100 billion. This is the miracle of 11N purity.
The polysilicon must be transformed into a single, perfect crystal. The silicon is melted completely inside a quartz crucible, heated to 1420 degrees Celsius. A tiny seed crystal is then gently touched to the surface of the molten silicon. As the seed is slowly rotated and pulled upward, the liquid silicon solidifies around it, growing into a cylindrical shape. This is the Czochralski process, invented by Jan Czochralski. The result is a massive single crystal silicon cylinder, the ingot, weighing hundreds of kilograms, with every atom arranged in perfect, flawless order.
The ingot is first ground to a precise diameter. A small notch is cut into the edge to mark the crystal orientation. Then comes slicing. A wire saw coated with diamond particles cuts the ingot into hundreds of thin, circular discs with extraordinary precision. For a 300-millimeter wafer, the thickness is approximately 775 micrometers, less than 1 millimeter. These freshly cut wafers are called as-cut wafers, but their surfaces are rough and damaged and not yet ready for semiconductor fabrication.
The sharp edges of freshly cut wafers can cause chipping and breakage. Edge grinding rounds and smooths the wafer perimeter to prevent damage. Next comes lapping. A slurry of abrasive particles and water is applied to both faces of the wafer, which is then pressed between 2 rotating polishing plates. This removes the surface waviness left by slicing and brings the wafer to a uniform thickness across its entire surface.
Even after mechanical polishing, an invisible layer of microscopic damage remains on the wafer surface. To remove it, the wafer undergoes etching, a chemical process where it is immersed in a strong acidic or alkaline solution. The damaged silicon layer is chemically dissolved away. With the mechanical stress removed, the wafer recovers its true, solid crystalline structure. Now comes the most critical step, CMP, or chemical mechanical planarization. The circuit features on today's AI chips are just a few nanometers wide. The wafer surface must therefore be flatter than any mirror. Using a precision polishing pad and a specialized chemical slurry, the wafer surface is refined to nanometer-level flatness. The chemical reaction softens the surface, while mechanical abrasion removes material simultaneously. The result is a flawless, mirror-like surface that reflects light perfectly.
The mirror-bright wafer is thoroughly cleaned using ultra-pure water and specialty chemicals to remove any remaining particles or metallic contaminants. Then comes the most rigorous final inspection. Laser scanners and optical instruments measure flatness, thickness, particle counts, surface defects, oxygen and carbon concentrations, and resistivity. Only wafers that pass every one of these strict criteria are sealed in specialized containers and shipped to customers.
The finished silicon wafers are shipped to global semiconductor fabs, companies like Samsung Electronics, SK Hynix, and TSMC. On this perfect canvas, hundreds to thousands of precise process steps are layered: lithography, etching, deposition, ion implantation, and more. After months of additional processing, the wafer is transformed into the cutting-edge AI chips and memory semiconductors that power our world. A single silicon wafer is never just a piece of silicon. From common sand, purified to 11N purity, grown into a perfect crystal, and refined to nanometer-level flatness, it represents months of relentless manufacturing and decades of accumulated human precision. The great innovations of the semiconductor industry all begin with this one flawless, mirror-flat silicon wafer.